Hello everyone, my name is Ratnadira. In this presentation I will talk about our paper called On the Influence of Biases in Bug Localization. As we all know, bugs occur in a project due to errors or mistakes in writing the source code or faults in its design. Several previous studies have found that bugs may also cause vulnerabilities, rendering the software susceptible to security attacks. Therefore, resolving bugs in a project is a high-priority task for developers. One of the solutions proposed by researchers is bug localization. Bug localization is the task of finding a part of the source code that needs to be modified to resolve a Most bug localization tools rely on information retrieval, where given a bug report, the tool finds and ranks the source code files that may contain bugs based on their relevancy. In 2014, Kochar et al. Highlighted the problems that exist in bug reports dataset that are used to evaluate bug localization techniques. This highlight the potential biases in bug localization. However, their investigation is limited to 3 Java projects. Moreover, newer datasets and bug localization techniques have been proposed and utilized without being checked against these 3 biases. It is unknown whether the newer datasetization technique is affected by the biases. Thus, further investigation on the impact of biases in bug localization is necessary. In summary, our contributions are as follows. We replicate Kochar et al.'s work by conducting an analysis on the effect of biases in a newer bug report dataset, focusing on projects containing Python buggy files in Bugsbook. We use Python as it is one of the most popular programming languages based on recent surveys and rankings. Contrary to its popularity, research and study on localizing bugs in Python files are fairly limited. We also release Captured, a bug report Python that has been cleaned from biases. In this study, we have 3 research questions. The first research question is how prevalent are the 3 biases? At the time of writing this paper, several new bug report datasets have been proposed. However, none of the currently available bug report datasets have been checked thoroughly to ensure that they are free from biases that have been pointed out by Kochar et al. We want to investigate whether these newer bug report dataset is also affected with the biases. We focus our study on the Python programming language, as it is currently one of the most popular programming language but only has limited number of bug report dataset. Choose Bugsbook to utilize the Bugsbook dataset that is built by Akbar and Kak, as it contains bug reports for Python code and has a bigger number of bug reports compared to the Bug.gl. First, we filter the bug reports by only taking the bug reports that fix Python files collected from Jira Issue Tracker. After this filtration, we obtain a total of 2,913 bug reports from 12 projects. Second, we clean the filtered bug report dataset from 3 biases. We will talk in detail about how we clean these 3 biases. First bias is the misclassified report investigation. An issue report may describe a bug, improvement request, documentation change, etc. Herzig and Zeller highlighted that there are many issue reports that are misclassified as a bug. In their study, they showed that the misclassification greatly impacts the experiments that determine whether a file is possibly buggy or not based on the history of past bugs. This is an example of a misclassified bug report. This bug report should be classified as an request for enhancement, as this bug report contains a request to give an additional option to separate the DBA mode. Next, let's discuss regarding bias 2, which already localized bug report. An localized bug report is a bug report where the locations of the files that need to be fixed are already mentioned in the bug report itself. As the bug report already contains the location of the bug fix, it means that the bug is already localized and does not require bug localization. We categorize the bug report into 3 categories, which are fully localized, partially localized, and not localized. This is the example for the not localized and fully localized bug report. As we can see, in the first one, the bug report do not mention of the fixed file which is params.py. For the fully localized one, the shared initialization is mentioned at the summary. Another issue which can bias the result is wrongly identified ground truth files. In bug report dataset, usually files that are changed in the commit as a response to a bug report are considered as the ground truth to evaluate the accuracy of bug localization techniques. However, there may some files that are changes, for example refactoring and cosmetic changes. But these files included in the ground truth. These wrongly identified ground truth files can potentially skew the result of existing bug localization solutions. We check bug reports that are not already localized and make modifications in more than one file. Amounting to 68 bug reports. We only check bug reports which contain more than one changed, since it is possible that not all of the changed files are relevant to the bug fix. This is the example where the file is non-buggy file. It is only cosmetic changes that did not include bug fixes, as the changes only replace the existing space with a new line without trailing space. These changes have no effect on the program output or execution. The result of the analysis is that we find 121 out of 2,488 bug reports are affected by bias 1. Then, 536 out of 2,367 bug reports are affected by bias 2. And 20 out of 68 bug reports are affected by bias 3. This distribution shows that newer dataset is also affected by the three biases. We name the dataset that have been cleaned from biases as captured. For the RQ2, we compare the performance of bug local on captured dataset which has been cleaned from biases against all bug reports from the corresponding projects in Bugsbook, which are not cleaned from biases. So, we run the bug localization on the dirty and clean dataset. We choose two bug localization techniques that are VSM-based that was used in evaluating bias in the previous study. And IncBL, a recent tool for incremental bug localization. We then compute the map, hit at N, and MRR, to evaluate the bug localization results. Following the previous work by Kochar, we use Mann-Whitney-Wilcoxon and compute Cohen's d-effect size to compare the bug localization result when evaluated using the clean and dirty dataset. For the map metric, the difference between the reported and actual for both techniques are also small. VSM-based technique achieves a higher score on the reported dataset, while IncBL achieves a higher score on the actual dataset. The results are in line with the hit at 1 and map, where we conclude that bias 1 does not statistically significantly and substantially affect bug localization results. The difference between the fully localized, partially localized, and not localized are high and can be spanned from 35 to 85%. We observe that the differences are statistically significant, except for the partially localized versus not localized bug reports. Meanwhile, the effect size results show that it spans from negligible to medium. The results between fully and partially localized versus not localized show that the difference is significant. For the bias 2 hit at 1 and MRR scores for both techniques are lower for the dataset with bias 2 removed compared to the one containing bias 2. We can see that the difference are substantial. The statistical analysis for MRR bias 2 significantly affects the bug localization results with small effect size. This finding shows that, for techniques, there are statistically significant differences between already localized and not localized bug reports. For bias 3, the differences in the map score between the dirty and cleaned dataset for the VSM-based bug localization tool are higher compared to IncBL. This is in line with the other metrics. The statistical test indicates that there are no significant differences between the results on dirty and cleaned dataset for both tools. The effect size also negligible. In this RQ3, we compare our evaluation done in RQ2 with the evaluation results of bug localization tool that have been done by Kochar et al. To compare results of the VSM-based bug localization technique. We conduct a qualitative analysis and found that we generally agree with the findings of the previous study, where only bias 2 has significant effect. However, the effect size of bias 2 in our dataset is smaller than the previous study. To conclude, we analyze the recent but report by Akbar and Kak. We specifically checked the bug report that fixed Python file, and found that the biases that highlighted by Kochar et al. Also affected this recent dataset. We also construct ad-release captured dataset that have been cleaned from the three biases. Found that bias 1 and bias 3 do not have significant impact for the results of bug localization. Meanwhile, bias 2 have significant impact. Our finding also in line with Kochar's study. However, we found that the effect size of bias 2 in our evaluation are lower compared to the study by Kochar. Thank you for listening to this